Hi everyone, my name is Shenan Liu. Today, I'm excited to share with you our work jointly done by a lot of colleagues, advised by Professor Yalin Yang and Professor Gang Wang. The name of it is called Stars Can Tell, a robust method to defend against GPS spoofing attacks using off-the-shelf chipsets. Today, billions of devices are receiving GPS signals, but in reality, GPS spoofing is a demonstrated concerning threat. Due to lack of authentication, if spoofed, GPS receivers get arbitrary location and time. For example, in 2017, ships were fooled by GPS spoofing in Black Sea. In 2018 and 2020, self-driving cars are diverted to dangerous roads. Back in 2011, researchers already pointed out stock servers are vulnerable to time asynchronicity caused by GPS spoofing. A more concerning trend is that spoofers are still evolving. First, they are getting cheaper. From the first demonstration of spoofer, which cost over $5,000, now an attacker can reproduce the attacks using about $35, and the hardware is commercial. The attack code is open source. Second, we are getting stronger. A naive spoofer achieves its goals by transmitting 40 dB higher spoofing signals. But now, more seamless attacks can be launched without causing anomalies during the takeover phase and the upcoming phases. Therefore, in our threat model, we consider the most powerful state-of-the-art single spoofer, and we require no physical alteration, hardware mounting, configuration change, or malware installation. The attack can only be launched remotely by transmitting wireless signals on the GPS channels. Although spoofer is cheaper and stronger, the anti-spoofing method still faces big trade-offs. Previous methods are either robust and expensive or cheap but ineffective. For example, receiver autonomous integrity monitoring. It can be implemented on smartphones, but it cannot defend against seamless attacks. Cross-checking with additional info sources, for example, like Wi-Fi, Bluetooth, cellular, other GNS systems which provide location, seem to be work. But previous study and commercial devices have demonstrated the feasibility of attacking wireless channels simultaneously. Sophisticated signal processing, they seem to be work as well, but it requires high-end software-defined radio and costing thousands of dollars. Angle of arrival is very robust, even when facing the seamless attacks. However, it also requires additional antenna arrays and high-end software-defined radio or other special hardwares. Crypto is the ultimate solution, but it requires the GPS system to upgrade to next generation, costing billions of dollars, and it can make the current GPS chipsets or not working. This naturally leads us to one question. Can a spoofing detector be both robust and low cost? The answer is yes. Other than crypto, angle arrival is the most effective way to detect GPS spoofing. Our goal is to derive angle arrival in a cost-friendly way. Our idea is to get angle arrivals by synthesizing a directional antenna array using omnidirectional antennas on commercial devices. For example, in the setting illustrated in the figure, we have a low-end hardware, the smartphone, equipped with omnidirectional antenna. Then we attach the receiver to a signal blocking material, human body, to make the antenna directional. We rotate the receiver with the blockage together. Then the signal strength fluctuates due to different receiver gain at different directions. For example, when facing the GPS signal source, we got the highest strength corresponding with the angle arrival. When back facing it, we got the lowest strength. And we can synthesize the angle arrivals from this fitted sine wave from a single satellite. By combining multiple satellites together, spoofing can be easily detected. Here we show two fitted sine wave plots, where the peaks are the angle arrivals we calculated, and the dashed lines are the ground truths. On the left side, different signals from different satellites spread apart, and the derived angle arrival is different. On the right side, however, spoofing signals with different satellite IDs, they align together, and all the angle rivals are the same. So this can help us to distinguish whether it's spoofing or non-spoofing. Based on this intuition, we propose 3 algorithms. The first method captures the difference between angle rival and the ground truth, which we call angle of ephemeris. To compute AoE, we need at least 3 things: on-device ephemeris file, current location, and time. But we realize that under spoofing case, there is no such thing as accurate location and time. So we also consider 2 other ways. Using the statistical patterns of these signals. The first is angle rival depth, which computes the deviation among different AoAs. And the next is the CN0 core, which is the time series of signal strengths. And then we compute the correlation between different satellites. We evaluated these different methods under different settings. We have 2 representative environments, open air and urban canyon. And we vary the blockage from human body to metal sheet. We also take ethics and legality issues seriously. For all the spoofing cases, we make sure the attacking signals are not emitted into the air, and they are either collected in the chamber or underground. Here comes our first evaluation on accuracy. We present the plot of ROC curve, which tells us the trade-off between false positive rate and true positive rate. All 3 methods, they achieve 100% true positive rate when the false positive rate is 0. In more sophisticated scenarios, 2 statistics-based approaches are sufficient good. The AoA depth and CN0 core present 100% true positive rate when the false positive rate is 0. The next thing we evaluated is detection accuracy versus time. In both settings, we achieved an accuracy of 100% in 5 seconds. Note that we are evaluating this on low-end chipset. And the report rate is as low as 1 Hz, which means the results are good when only 5 samples are considered. We can definitely accelerate this process by using a higher-end chipset, which reports in 10 Hz or 50 Hz. And this achieves our first goal. We are able to detect the strongest spoofer in a robust but cheap way. Let's take one step further. What if the spoofer is aware of these defenses? Let's stand in the attacker's shoes. What will they do if they want to get around with our defenses? They might mimic the different rotating signal patterns. Still, the attacker has no direct access or visibility to the internal software or hardware of the GPS receiver. So the attackers have to guess the rotation speed and the initial facing angle of the GPS and modulate the signals accordingly. This makes them able to simulate the adaptive sine waves. So what would we do to defend against it? The defender can change the rotation speed in real time. So the rotation speed of the GPS receiver is inherently a secret that can be dynamically changed by the defender. For example, the correct guess of rotation speed and initial angles result in unaligned signals when fitting the sine waves, which pass through our defenses. However, incorrect guess of rotation speed or phasing angle can lead to inauthentic signal patterns. This observation inspired our first detection method. It is called average over the cycle. The main intuition is that when rotating multiple cycles, we can actually average out the incorrect guess on the phase domain. Through rotating many cycles, slicing them into many different degree slots, and average the measurements in each slot. When we rotate as many cycles as possible, we can actually average out the modulated signals in the fitting process, and they will only leave the rotating signals inside. Our next method is called spectrum analysis. The intuition is simple. we found that the rotation and the modulation waves, they actually have different frequency components. And by decompose these kind of frequency components, we can not only detect whether there is an attack or not, but we can also get the phase, the unmodulated phase from the spoofer, which means we can identify the angle of arrival from the different satellites, as well as the spoofing signals. We evaluated once again the accuracy of the detection methods. When we apply the adaptive spoofing attack against basic detection, we found that those two previous methods perform really bad on this classification problem. However, when we are using the advanced detection methods, they actually got a lot better, especially when you are looking at the open air cases, and you can perform quite well on urban canyon cases. And we also evaluated the time to deal with it. And you can see now we might need more time to deal with it, but we can also achieve our goals within 30 seconds. Here comes our takeaways. We propose a new method for GPS spoofing detection that works on off-the-shelf GPS chipsets. And we explored both basic attacks and adaptive attacks, and introduced additional measures to fortify the defense. We implemented proposed methods and the adaptive attacks. Our method achieves a high accuracy in 5 seconds. Thanks everyone for your attention. One more thing is that we open sourced our code, dataset, and Android app. Please feel free to scan this QR code if you have any kind of further question, and you can access our contacts, paper, code, dataset, Android app in it. Thank you so much.